speaker is Olivier Goffart. He worked for Trolltech for a longer time now, and now he's co-founder of a small startup company here in Berlin. And he will talk to us about QtCore in that. He wrote a lot of stuff in QtCore, so he's probably one of the best person to ask questions about QtCore. So please, a huge round of applause.
Hello. Yeah. Welcome. So just a bit about myself before starting. So yeah, I got an introduction, but I did one myself. So I'm originally from Belgium, from Liège, French-speaking city. So excuse my accent. Sorry for that. As a student, I was developing on QtDD, which led me later to be hired by Trolltech to work on Qt, then Nokia. And yeah, I was working in many areas in the Qt framework within Nokia. And last year I started a company, so we're two in that company, and we're offering Qt services. And one of our products also is this code browser, which I'm going to even use in this presentation. So in this presentation, I selected few parts of QtCore. I'll talk about the event loop, private implementation, the containers, and a bit of how signals and slots are implemented. There's so many things in QtCore that it's not possible to fit everything in a talk. I talked about threading last year at Dev Days. There is a talk about QVariant and QMetatype later today. But this is going to be a technical talk. So I'm going to see the real source code of Qt, and we'll see how some stuff are implemented that might help you to yourself develop application with Qt, knowing a bit on how it works and what to do and not to do. So let's start with the event loop. So for that, I have a small application. It's written in QML, and I'm going to just click there. Yeah, a crash. That's expected because let's just make some room here. So I just, here my value is 0, so then I divide by 0, I have a crash. But what I'm interested in here is the backtrace. So you might have seen this in your own applications, stuff like Qt static meta call, QObject activate, and I'm going to explain what it is all about. But let's go back to the beginning of the backtrace, to the main. And as most Qt applications are done, you just instantiate an application and you run exec. And that is the event loop. So application exec calls QCore application exec indirectly, which do some initialization, and just creates one of those Q event loop class that you could also use within your application, within one thread, or even to re-enter the event loop, which I do not recommend, by the way, but you could do that. And so QCore application exec will just call exec on this event loop. And that's just a loop. Nothing special about that. A loop that will process the event. And process the event is just delegated to the Q event, to the QAbstract event dispatcher. QAbstract event dispatcher, that is an abstract class which can be re-implemented. And in Qt, we have re-implementation of it for each platform. And here we use, if you see the backtrace, we use this QA event dispatcher glib, which integrate with the glib event loop. That's the default abstract dispatcher on Linux. Why is that? That's because we want to integrate with the GTK. Like if you want to run the GTK style, then we need to be integrated with the GTK event loop. If you have other plugin written with glib, then you need to integrate with this event loop. And this is also one of the good points about Qt, that you can integrate with any other event loop. If you have your own library or another third-party library that has its own event loop, you could even write your own Q event dispatcher for this to integrate with that event loop. And then the event, so here I clicked, and it's an event from the window manager or the windowing system. So there are three main sources of events in Qt. One of them is the events coming from the windowing system, all the inputs. Another source of events are the timers. So if you use a QTimer, if you call start timer on an object, then that's another source of event. And the third source of event will be the event you post yourself with QApplication post event, or with the signal, the Qt connection with the signals and slots. That's also events posted to the event loop. So this talk is about QtCore, not QtGUI, but that's not how I had it before. Okay. So this talk is about QtCore, not QtGUI, but in Qt5 we use XCB for the as the windowing system, as a library to connect to X11. And how this event work? We have this thread here which will poll for events in a different thread, and then all the events will be forwarded to the main thread. And then let's go back to our backtrace. Sorry, the font is a bit small, but I can't increase it. Then the event will be forwarded to QApplication notify, and then to all the way up to the QWidget event, which will then forward it to QDeclarative and all the way up. Then we're connected here to a slot, and that will be for the last part of this talk. So yes, that's a short introduction about the event loop. As I said, there's a lot to talk about, but is there any? Oh, let's move to the private implementation. So by private implementation, I mean those D pointers. In C++, you have classes, and those classes can have public members and private members. You know that, but we don't use really private members in Qt, and one of the main reasons is to maintain binary compatibility. If you add or remove private members or change them, then you change the size of the class, and that's a problem. Why is that? Because your application, if you compile your application with Qt 5.0 and you want to instantiate a QString, for example, and the size of QString is maybe 8 bytes, and then when you instantiate the QString, the compiler will know I need to allocate 8 bytes there before calling the QString constructor. Then if the size of QString has changed in Qt 5.1, and you run the same application against Qt 5.1, then we will still allocate 8 bytes. The application doesn't know it has changed, and before calling the QString constructor, which expects a different size, and then most likely you get a crash or some other weird bug that you don't even know why it crashes, but that's binary compatibility. And so the way we solve that problem in a way is by saying all our objects in Qt or almost all the objects in Qt are just the size of a pointer, this D pointer. So we have this, for every class foo, we have this foo private class, which is forward declared in the header. And then in the CPP file or in a private header, then we declare all our private member. Another good effect of that is that if your private member are maybe objects that you don't want to include the header of this object within your public headers, and so it reduces the compilation time. The drawback is that you will need to allocate one of those private implementation for each class. And how we solve that? So for example, if you have QLineEdit, you don't want to both allocate QLineEdit private, QWidget private, QObject private. That's 3 allocations. So we optimize that by mirroring the hierarchy in the private. So then in the constructor of QLineEdit, we allocate QLineEdit private, and we pass that to the constructor of QWidget. So then we don't need to reallocate another QWidget private or another QObject private. So that's only one allocation, even if you have 3 objects in your class hierarchy. And we also use some macros to help us. So for example, here I have the class QTimeline. Oh, I increase the font. QTimeline, as you can see in the public header, we forward declared QObject private. And we have here a macro at the end. We say QDeclare private. And QDeclare private is a macro that will implement some helper function, as well as marking the class as a friend. We also do have a defunc, which will give the right type by doing a reinterpret cast here. Here in the implementation of QTimeline private, we have the macro QDeclare public, which do the same. But here we have a QFunc with a static cast. And that helps. So in every function, for example, this function within QTimeline private, we just have start with QQ, which just creates a QObject, which then we can use, in the function. And then in public function, then we have the same QD, which call this helper function declared in QDeclare private, and then we can use this D pointer. And you will see that all over Qt code. It's all using this same paradigm. So what little details about those macros. So QDeclare private use reinterpret cast, and QDeclare public use static cast. So the question is, why do we need to use reinterpret cast here? Do you have any idea? And the reason we need to use reinterpret cast in QDeclare private is that because QDeclare private is supposed to be in the public header, where the class private is only forward declared. So we cannot use static cast with only forward declared class. So this is why here we use reinterpret cast. Any question about the private implementation? And this idea of private implementations allow one of the main concepts of the class that can be copied. That in Qt we do implicit sharing. So this, so what we just saw now was for all the objects that you are mostly using by pointers, but for all the other objects that you use on the stack and that you copy around, like QString and most of the Qt classes, then we use this idea to have only one instance of the private implementation for every instance of the QString that refer to the same string. So when you copy, there is a reference count within the private class, and when you copy a string, you just increase the reference count, and you just detach it when you modify it. That's copy and write. Let's move now to an explanation about the containers. What are the different containers and how are they different, especially when you see QList or QVector, what are they, or when should you use QList, when should you use QVector? So let's look at their implementation. So I'm stealing those images from one of the Qt quarterly articles that was released shortly after QtCore. So just take a picture of this and or just Google for it. It explains how the containers in Qt4.0 works. This has changed a bit, but it's still mostly the same. So here we see how QList and QVector are represented. So this first one here is QVector. As we can see here, it's implicitly shared. So we have 3 QVectors that are referencing the same data with this ref count, which is the number, which in that case will be 3. And same for QList, but the difference is that in QVector, the elements are directly stored within the array, while in QList we have an array of void star, and it's a lot of pointers to the actual element. The rationale for doing that is that when you insert something in the middle of a QList, it's faster to move the pointers than moving all the elements, or it was supposed to be like that. And the other difference is here in QVector we have a size, and in QList we have a begin and an end. Both of them have an alloc, which is the size of this array, how much size is allocated there. It's not the same as the size, because we allocate more space than required. And the reason we do that is so then when you append stuff in your vector, it's really fast. You don't need to reallocate all the time, only when you reach out of space. And in QVector, you only have space at the end. But in QList, since you have a begin and an end, then you have spaces both in the begin and so before and after. So you can append or prepend or remove from the beginning or remove from the end very quickly in a QList, while QVector has to move all the elements around if you append at the end or if you prepend. So QList will be better for something like a queue, while QVector will be better for a stack for this reason. And another difference in QList, because the arrays are always the size of a vector, then we could share this implementation in this QList data. All those functions are implemented in this QList.cpp, while in QVector everything is implemented in the QVector.h, because everything depends on your actual elements, all the allocation, the moving around of the elements. So for that reason, QList is supposedly to take less size in your binary than QVector. There is an important optimization, however. In QList, if your items are small enough and movable, so that means they have a trivial copy constructor. It's not that simple, but then in QList we can just store the elements within the in the array. So then it behaves exactly like a QVector. You see that a lot. So in order to know when to do that, we use this class QtypeInfo. And QtypeInfo is just an implementation details. We have it tells us, so it's a type threads in a way. So for each type, it tells us if it's a pointer, if it's large, or if it's complex, which means it needs to be constructed and destructed. If it's static, which means can it be moved. If it's not static, it means it can be moved by just memmove. And how do we detect that? Well, we have those specialization. For example, for the pointer, we know that they're not complex, they're not static, they're pointers. And in your code, you can do stuff like qdeclare type info with your type. For example, if you have your own type and you know that there is no need to call the copy constructor, you can just move the memory bit from bit. Then you can call qdeclare type info, which will do a specialization for your type of this qtype info. And you can, for example, say movable type, which will enable this optimization in QList and also in QVector. Then QVector do not need to call the copying constructor. It can just move the memory around when you insert element in the middle. So this little qdeclare type info might be very useful for optimizing the Qt containers. Unfortunately, we are not able to detect automatically whether we can do or not this optimization, because the C++ standard do not have this in C++ 98, which we still support. In C++ 11, there are those type threads that will allow us to automatically detect that, but we can't use them in Qt, unfortunately. Is there questions? No. Some other sequential containers which I want to mention but not really talk about are qvar length array and qlinked list. Qvar length array, first, you can use it if you know that you will have you're likely to have a small number of elements that you can put on the stack, and if it exceeds this number of elements, then it will only allocate on the heap if it's required. And it's behaving a bit like a vector otherwise, and qlinked list is a linked list. Then let's talk about associative containers like qmap. It's a tree. At least it's a tree in Qt 5, because in Qt 4 it was a bit more complex. It's called a skip list. It's like you have several levels, and when you look at an element, you can quickly because all your elements in qmaps are sorted. So the key of your qmap needs to have this operator less than, and then we use this kind of way to search, which is supposed to work in a logarithmic time. But we changed that in Qt 4, and we changed that in Qt 5, and in Qt 5 it's now a red-black tree. And then we have qhash, which is just a hash table. So you have a list of buckets. For your key, you compute a hash, just an integer, and then modulo n, and we look it up, and if there is a collision, then it's implemented as a linked list. Yeah, which means the worst, if you had a collision on every element, then the worst case would be O(n) to look it up. But usually, if your hash function is well done, then it will be O(1). So let's do. I made some benchmark here. So the benchmark that I just have some function that instantiate the containers of QString that loop for half a second and see how many iterations it can do. And I did that for some containers with Qt 4.8. So those containers that are mostly constant time as qhash and std unordered map, as you can see, they're about the same. And then here is depending on the number of elements there. And then as you can see, qmap gets slower and slower the more you have elements, and like between around 10 elements, then you should better store into a qhash. That was in 4.8. In Qt 5, we changed the implementation of qmap, and then qmap is aligned again against std map, and we're like 32 elements. But as soon as you have many elements, then qhash will likely to be faster. Yep. Let's talk a bit about QString and QByteArray. I don't want to go too much on the detail. Just what I want to say is that in Qt5 we shared the implementation between QString, QByteArray, and QVector. We have this new class QArrayData. It's just internal implementation because QString is just a vector of QChar and QByteArray is just a vector of char, and then most of the logic behind is the same, just with different types. So we shared the implementation. And yeah, it's also allowed us in Qt5 to do QString literal and QByteArray literal, which allows to generate a QString at compile time without any overheads, any allocation or anything to convert to QString. And then the smart pointers. In modern C++ code, you should almost never call any delete because you don't want to do the memory management yourself. We're C++, it's not C. So you should use smart pointer. You have some smart pointer in Qt. QShared pointer will just you have a reference count and it will keep track of the reference count of your object. And you have QWeak pointer that will hold a reference that is just a reference to a QShared pointer but without holding the reference, which means if all the QShared pointer runs out of scope, your object will be deleted and the QWeak pointer will be notified and will become 0. We have QPointer that's a bit like QWeak pointer, and QPointer is used to track QObject. It exists since Qt4 and even since Qt3 under a different name, and its implementation in Qt4 was a bit weak, a bit too slow, and we noticed that while working with QML, and they used a lot QPointer and it was too slow for them, and we couldn't change anything because of binary compatibility. So we tried, because we thought QWeak pointer, that's a bit the same semantics, so we tried to hook the possibility to track QObject within QWeak pointer. But then we noticed that QWeak pointer is meant to work with QShared pointer, and there is still some differences in the API, and that it was a bad idea to use the same class for both. So now in Qt5, we deprecated the usage of QWeak pointer to track QObjects, and we recommend to use QPointer, which has been properly optimized in Qt5. And then, so let's go back to our example here. Signal slots, how do they work? I have here the mock generated code. Oops, I'll just change to creator. So when you have one file like that, so you have some macro here, like QObject. What is QObject? It's a lot of things. And all those functions like metaObjects and stuff that are declared within this QObject macro, all those functions are implemented by the code generated by mock. And how does mock knows what are the slots, for example? Then it looked for this macro. This macro, when compiling to C++, it just expands to nothing, but the mock still sees it. Signal means public. It used to mean protected in Qt4, but now it's public, and the reason for that is the new connection syntax. I'll talk about that later. So signals and slots are just simple function. For example, signal is implemented by the generated code, and it's something like that. So that's the code generated by mock. So it went and generated this signal, and what it does, it just call activate, QMetaObject activate, with some parameters. So the metaObject the signal index, which in this case I only have one signal in my object, and it's the signal 0, so then it's the signal index, and this array of parameters. So it's an array of pointers to the actual parameters. So here I only have one argument, t1. I just take the address, make it const void, and pass it to QObject, to QmetaObject activate. So I go to this QmetaObject activate. There is one indirection here. We just call activate again. That's because QDeclarative uses this one, but it's just a small indirection. And what we have we have local signal index, and we have the signal offsets. So a bit more about those offsets. So there, for example, for QTimeline, we have the indexes, the relative indexes for all the methods that are known to mock. First comes the signals, 4 signals, and then comes the slots. And they have this this index. But that's relative indexes. When you take an instance of QTimeline, it inherits from QObject, and QObject has some signals and slots too. So then the absolute indexes for the methods, it's just we add some offsets to them, so the method offsets. And those absolute indexes are the one you can see from the public API if you call QmetaObject index of signals or index of slots. Then the index it returns is this absolute index. But because the signals are going to be indexed in an array, then and there's often so much more slots than signals, then we have this other indexes called the signal index, which is we just removed all the slots, and this is only used internally. So then when you call activate, the first things we do is we check is signal connected. And this one will just take the signal index, so not the slots, and we'll look into this connected signal that's within our QObject private. Here we have this within QObject private, we have this array of twice 32 bits, so 64 bits, which we use to quickly check if the bit is 1 for this signal, then there might be something connected. But if it's 0, then we know there is nothing connected. So that means we can really quickly really quickly find if the signal is connected to nothing, to quickly return. So that means emitting a signal that is connected to nothing will be really fast. Just one call to activate and one other call to activate, and then we check, and then we don't need to do any other lookup. Then there are some other hook done by declarative here. That's because declarative wanted to do their own way, and then we have this code. But in the general case, when we emit the signal, we have to lock the data structure, and the data structure look like this. So here in the in the QObject private of our senders, we have a connection list, which is a vector for each signal. So for example, here the signal 4. Then it's a linked list of connections. So we go and go to iterate over this list of connection. This list of connection contains all we need to send the signals. So when we connect, we create this list of connection. It knows the receiver. It knows the slot index. So it can call activate, and there's also this, and this is used when you connect to a function pointer. I'll talk about that later. And then you have the next in the connection list, and then you have also this double linked list for the sender. So each connection here is in 2 linked lists, which allows the fact that it's linked list allows to destroy the object fast, because it used to be vectors. We had the receiver had a vectors of all the connections, but then it turns out to be really slow when you had a lot of objects connected to each other, and then when you remove objects, it will be n squared to when the objects are destroyed, to destroy all the connection, because when you destroy an object, you want to automatically disconnect everything. So we need to keep this list of senders, and the fact that it's a linked list makes easy when you just have the pointer to the connection to remove it from the linked list. And it's a bit different from the linked list we see at school, where you have a pointer to the previous and a pointer to the next. Because you don't have a pointer to the previous, you have it's not a single pointer, it's a pointer to a pointer. So what this previous actually is, it's a pointer to this. It's a pointer to the next. It's a pointer to next in the previous connection. So this kind of little trick here allows us to not to have any special case for the first element, because the first element just in the QObject private here, you just have a pointer to the first, and the previous of the first is just a pointer to this first pointer here. So back in our activate, then we can call this. For each connection, we look what it is. If it's a Qt connection, or if the threads are in different, or if the objects are in different threads, we'll do a Qt connection, a Qt activate. So Qt activate will copy using QMetatype. We will copy all the arguments into a separate array, and we will create an event that will be posted to be later in the next iteration of the event loop. We will call the function. But if it's a direct connection, what we do is to call this call function, and this call function is a pointer to the the Qt static meta call. It's set in the constructor, so it's part here of my connection, and so this will call the QStatic meta call with the receiver. We want to invoke a method. We have the relative index, and we have the argument. So back in the mock generated code, we have QtStatic meta call here. Remember, the call was invoke meta method. The index, so if we were connected to slot clicked, the index was likely to be 3, or no, to be 2, sorry. and then we call this way, and we cast back the arguments to the previous value. One of the questions I had before was, how does it work if you connect a slot, or if you connect a signal that has maybe 5 arguments to a slot that only has 1? And the answer is we just ignore more than all the other arguments. So here, this if this array had like 5 arguments because it was connected from a signal that had 5 arguments, then we only use the first one if we have only 1 argument in our slot. And then I can speak about the new connection syntax in Qt5. You might have heard about it in other talks, but we can do better here. So I will not crash here, just. So so my program was just, I had this this root object comes from the QML, so it's just a QML signal connected to my slot clicked signal, and then the slot clicked signal emits my signal, and we connected my signal to another slot, and that's how you will do in Qt4, and you can still do it in Qt5. But what you can do in Qt5 is to use my signal is to use function pointer. So this syntax might be a bit weird at first, but you could quickly get used to it, and it's a standard C++ for forever, just not part maybe of the subsets of C++ people are used to it with Qt. But you can specify a pointer to member function like this. And then let's run. Up 0 because value was 0 here. And then it why is that better? Because if you do a typo here, you do some typo, then it will only be seen at runtime. Then you will have a warning saying while you run, if you look at the output, you will have warning there was no signal clicked, and if you're lucky you see it. And but here if you misspell my signal and you try to compile, what you will get is an error. There was no signal. So you get compile time check that it works. And another side effect is before you had to have the exact same type. So here my signal was taking an int and the slot was also taking an int, but now with this new syntax, because it's all done with templated code, then we can see that there's an implicit conversion from int to qvariant. And even if your slot take a variant, it will still do the connection. And as you see, it just converted the int to a variant. Could it be a qstring? Nope. And you get a compile time error saying assertion failure. The signals as slot arguments are not compatible, which you get at compile time instead of at runtime. And this is C++ 98 code. I've often heard, look, now in C++ 11 you can do this new connection syntax. It's not this part is not C++ 11. It's the plain old C++. Then, if you use C++ 11, there is another really nice thing that are the lambda functions. So this part is C++11. So that might be new to you, this kind of funny braces. But that's a lambda function. It's new in C++11, and you don't have, when you have a slot that only contains one line, you don't need to create your slots and implement it. You can just implement it on inline and then so how does all of this work? Or is there any question on this? Can you use them?
Any questions, please ask for the microphone. Okay.
Where does type OBJ come from? Okay.
Yes. So yeah, that's yeah. Does that answer your question? It's just this is just the syntax to member to pointer to member function. So you just say my type. So for example, you could also say QObject destroyed. That's also one. And then I guess then when you quit, it got destroyed. And yeah, that's just the syntax for member function. You just say type : your function. Yes, question over any question?
How would you disconnect a lambda function?
Good point. And then when I quit, I don't get the hello. What is this? This auto, so this auto is C++11, but that's I think QObject connection. So you can keep reference to your connection and disconnect them that way. More question there?
It's a related question. How can be lambda function connected if it is not member function of any object? How the bookkeeping of signal slot connection is keyed inside of Qt?
For lambda function or in general?
For lambda, we have seen how it is done in general, but I cannot imagine it for lambda function.
We'll have a look at that. So this is with lambda function. This is how it's implemented. We just have this this QFunctor slots. So this QFunctor slots it inherits from QSlot base, and so that's all internal details. So QSlot base is a class. So each time you connect, we create a new QSlot base, but it's an abstract class. And it's not implemented with virtual function because virtual function are a bit expensive. So it's implemented without virtual function, but the same. Imagine you have a virtual function here, and this Q. So where were we? So this QFunctor slot object has it's a template class. This func here is the type of your functor. Lambda expression are just functor, and we store it within this functor slot object, which is allocated on the heap. And then within the QObject code, we call this this function got called for the QObject with those arguments, and then we forward to some other template code to do the actual call. So it's basically stored in this slot object with it, which is allocated on the heap with a copy of the functor. Does that answer the question? Okay. What any details you would like to?
Does this connecting to lambdas also work with variable capture and stuff like that?
Yes. So variable capture is, so I go back to the case where I was connecting to another slot. And I can have like, and I can even access this from my function. So I just, here is the capture, which means which variables are accessible from within the lambda function, and then I can use it there. And I can even capture by reference. So then if I modify it here, so yeah, you can access, you can capture in a way this int within your lambda function.
In this case, I have next question. Does that mean that you cannot use Qt connection for lambda functions?
Yes, you cannot.
Thank you.
Yeah, we could implement it maybe, but as currently you can't use Qt connection for lambda function, but you can use it for the other syntax. So you can, but not for lambda function.
Yeah.
In case I have more parameters in single than one compared in slot, the case we were talking before, can I use the new way of connecting single and slot?
Yes.
It's still okay. Thanks.
And no, no, it's not the case here. But yes, you can. The same, yeah. The only difference is that you cannot. So, for example, here my signal has a or before the slots might have a default parameter, and it's not working anymore to connect a slot as a signal without arguments to a slot with default parameter. Yeah, that you cannot do anymore. So else, well. So yeah, if you have more questions you can about anything, you can just ask.
How explicit do I have to be when I specify using the new old C98 function pointer syntax? Like you use the QObject destroyed signal. Could I also write object destroyed? Because object inherits from QObject. Does that
Yes,
work, or
that works? Yes.
Okay, thanks.
Yeah.
Hi. If we have one signal connected to multiple slots, in which order will the slots be called?
Yeah. So it's basically the order you connected them to. So if you start connecting slot 1 and then you connect slot 2, it will be slot 1 and then slot 2. So there's a bit of history behind that it has always worked that way, but we decided not to document it, or the one that did the implementation, because he decided that could change in order to optimize, we could maybe change the order. But people have started relying on this, and then I thought we also have unit tests that make sure that it's the case. So I thought let's document it, let's mark it in the stone. So then that's because then you can rely on it. Yes. So then if you start connecting your signal to slot 1 and then to slot 2, then it will be in that order: slot 1 and slot 2.
So, any more questions? We have some other minutes. No? Okay, I say not. Okay, well, many thanks to Olivier for coming here today. Please.